So just to explain how the video goes, we've recorded all of these client-server interactions already, and now we're just going to play back the video of these interactions. And I'm going to be playing and pausing this video and using my pen to mark up and talk you through the different aspects of the interaction. And then on the left side will always be the client in black, and on the right side will always be the server in gray. The server here is running on a virtual machine on the same laptop as my client. So again, on the left side here, we have the client interface. On the right side here, we have the server log. And then here we also have the content that's stored at the server. So we have a file here called file1. File1 contains the content right here, which is the alphabet right here. So let's roll the video. So there's a few main points to see here. The first is that we ask, since it isn't cached, we ask for service ID 6 from the server, which is the last edit time at the server. The last time the file1 got edited at the server. And the other thing that we ask for is, obviously, since it isn't cached, we have to ask for the content itself, and that's service ID number 1. And after getting that, we print it to the console. So the first thing to note here is this option of 900,000 milliseconds, which is 15 minutes, which we've set as the freshness interval for the client. So if we read the content once and then we read it again within 15 minutes, then we will just read from the cache. And so that's what we're going to show here. So things to notice here is this is the first time that we call read. And for this one, we have to read it from the server as indicated by the 2 requests that we make. One for service ID 6, which is the last edit time at the server, and one service ID 1, which is the actual read content. And then here, the second time that we read it, notice that there are no service IDs requested from the server. And so since we've determined that it's fresh locally, since the time that we checked in with the server minus the current time is less than this 900,000 seconds that we've set as the freshness interval, then we can just read straight from our cache. And so it's printed here. So here we've set our freshness interval to 5,000 milliseconds, or 5 seconds, which means that if we read once and then we read that same thing again, after 5 seconds have passed, then we will have to check in with the server to see if it has expired at the server. So let's roll the video. So again, this is our first time reading the content, so we have to read it from the server. Here, the second time we read from the server, we notice that it's not fresh locally, since the current time minus the last time we checked in with the server is greater than our freshness interval. And so we request service ID 6, which is to get the last edit time from the server. And we realize that the two edit times have matched. The edit time at the server and the last edit time at the server that we know of, that we've stored in our cache. So therefore it's fresh at the server, no need to read from it, and so we grab the content straight from the cache. So here we have two clients. We have the first client, we have the second client. And for both, we've set the freshness interval to 5 seconds. And so what client 1 is going to do is client 1 is going to read twice. And upon the second read, client 1 is going to have to check in with the server for the last edit time and realize that during that time, client 2 has written to it. And so client 1 is going to have to end up reading from the server again. So a few things to notice is that first we check the freshness interval by comparing these two times. We realize that it's not fresh locally, and so we get the last edit time by calling request or service ID 6. We get the last edit time at the server. We compare that last edit time with the last edit time that we have, that we are aware of. Since they're different, we know that it's not fresh at the server and that we have to read from the server. And so that's when we call service ID 1, which is the read service, and we find the new content here, which we print out. So here we have, instead of the file content, we have the root directory for our file system. And so here we have two directories, dir A and dir B, and we are going to try to read content from dir A. So as you can see, after calling service ID 1, which is reading the content, we get an error from the server that is not a file. That matches up with the server's log right here. So part of the client-server communication protocol is that whenever we read content, we read via blocks. And so the blocks mean that if we are to read, let's say, 250 bytes, we're going to send those 250 bytes in blocks of 100. And so the 0th byte in the file always corresponds with the start of the 0th block of that file. So we're just going to go forward in increments of that block size. So in this case, our block size is size 100. And so in this example, what's going to happen is the client is going to read from the server a first time. And upon reading it the first time, he's going to realize that the content read, the content that the server returns, is less than the block size, right? Because the content right here is 27 characters long. And since the block size is 100 and we only got 27 characters back, we know that these 27 characters, this block, this 0th block, has to be the final block of the file. And so when we go to read it a second time, when we go to read the content a second time, we're going to ask for a range that is out of bounds. And so instead of getting an out of bounds error from the server, we can figure it out at the client that it is out of bounds already, since we know that the final block is the 0th block. So this is the first time that we read from the server, or we try to read the content, and we ask for offset 0 and byte count 10, which is very much valid. It's about these characters right here, or right here. But then during the second time reading, we ask for offset 0 and byte count 30, which is obviously out of bounds, or bad range. And so since when we read the first time, our final block was set to 0, we know for a fact that there is no content after this right here, after this Z, which means that when we ask for offset 0, byte count 30, we know at the client that it's the bad range, and so there's no need to ask the server. And so we return bad range without ever having to contact the server. So last time we figured out that the range that the client has asked for was bad. And we figured that out at the client without ever having to contact the server. So this example is just to figure out, or just to show an example of a bad range error, but only figured out at the server. So here, again, the content is just the alphabet. We ask for offset 0, byte count 100, clearly out of range. That's what you get. So here we're going to show an example of the write service. So again, here we have the content of the file called file1. File1 is at the server, and we're going to write to it. And so after writing this new content at offset 0, we see it appear in the file at the server. So here we have two clients. This is the first client, this is the second client. Again, here is the file that we're using, file1. And file1 just contains the alphabet right now. And so we're going to check out the monitor service. And this client 1 is going to be the one monitoring, and then client 2 is going to be the one making updates to the same file that client 1 is monitoring. So the main things to notice is that we've set our monitor time to 60 milliseconds or 8 minutes. And after client 2 writes to file 1, client 2 writes to file 1, The first time being hello world. Then client 1 receives an update. And then the second time, when client 2 writes more updates here to an offset of 0, the first client also receives that update. So the clear service is fairly straightforward. Again, here we have the content of file 1, and we will try and clear this file. So you can see the file has been cleared after we indicate service ID 4, which is the ID to clear. This is the example for the trim service. So again, we start with the alphabet in the file, and then after calling service ID 1, or service ID 5, which is the ID for trim, we're going to check the file again and see that the letter Z is no longer there because we have trimmed it. So one thing to notice is that sometimes you will be deleting the last line, or the new line, rather than deleting an actual letter that's visible in the file. So here we started with the Z of the alphabet, the Z being the last character, and deleted that. Sometimes you might think that trim doesn't work when instead it's just deleting the last line, the new line. So this is the second example for trim. We're just going to show one of the errors that can pop up, which is if you try to trim from an empty file. So you can see here that the file is already empty. And as such, we get a file is empty error. This is the example video for the create service, which creates a new file. So before, our service only had file 1. After calling service ID 8, we now get file 2. For the example for the remove service, we're going to continue the example as before. So here we have file 1 and file 2, and we will call on service ID 9 to remove that file. So here is the example video for the list service. So here we have all of the files and directories in the root directory for the file system, and that is what we're going to try and list. So we use the slash to indicate the root directory, and we get these as our result. So the directories are marked with the dir, and then the files are marked with file. So here is the example video for non-idempotent operations on at least once invocation semantics. And so here we've indicated a failure rate of 0.3 from the server, which means 0.3% of the time, the server is going to pretend that it's failed to send a packet back to the client. And so we're going to try a non-idempotent operation, in this case the trim operation, which removes the last character from the file content being right here under, again, the file name file1. And so here we've indicated service 5 for trimming, and as you can see, the message is sent, but we've simulated a failure here. So the message is sent without it getting received. So as you can see, we had a socket timeout twice, and both times we resent the message, and on our second resend, we got a reply, and at that point we finished service ID 5. And let's examine the new content right here. So whereas before we had Y, and then Z, and then new line, that's supposed to say new line. Since we ended up sending the same message 3 times at least once semantics, we ended up deleting 3 characters instead of just 1, which is not our intended effect. So here we're still doing the at least once invocation semantics. Again, we have a failure rate of 0.3, which means 0.3% of the time the server is going to simulate failing to send a packet back to the client. But this time we're going to do this on an idempotent operation, which means if we do it multiple times, it is the same effect as if we did it once. So the non-idempotent operation of choice here is the clear operation, which clears all of the content in this file here. So here we had 1 socket timeout, which amounted to twice the message getting sent. But since the operation was idempotent, the clear ended up happening twice, but it has the same effect as if we cleared just once. And we do get the desired effect over here. So here we are going to use at most invocation semantics, again with a failure rate of 0.3. And we are going to use at most semantics on the non-idempotent operation of trim, where again we just remove the last character in a file. And so what happens is we send the message, our server has simulated a failure, and then so on timing out we send another message, and then on the server side, the server sees that it has received the same request again. So instead of recomputing that request, it resends that message that it had already, or that reply that it had already generated. And so on receiving this reply, the client acknowledges it, And in that, after that happens, the server removes that request from its list. And then, since this was at most once invocation semantics, even though we ended up sending the trim request twice, we only ended up removing one character, specifically the Z character. Here we have at most once invocation semantics for an idempotent operation, and our idempotent operation will be the clear operation. So here, after setting our invocation semantics to at most, we have indicated that we want to clear this file. We send it once. Failure is simulated. So we time out and send the message again. The server notices that it's a duplicate request and then resend this reply. Upon receiving our reply, we send an acknowledgement, and then that acknowledgement is removed from the stored list. And the effect is a clear file.